Okay, so section 1.5 is about polynomials, parametric functions, and combination of functions. Okay, so these are things that you've probably seen before, but we're going to emphasize a few ideas that, just to make sure that you have these ideas. Okay, so polynomials, right? What's a polynomial? Somebody tell me what a polynomial is. Can you tell me what a polynomial is? Cynthia.
It's a function with more than one variable.
Okay.
I don't know exact.
It's sort of hard to
more
describe.
than one variable x, I guess.
Okay, so it's a function. It has some x's in it, maybe. Alfred?
So like multiple powers.
Could have powers of x, right? So you could have so here's sort of like the mathematical way that one describes a polynomial. Any function of the form f of x, I would say p of x, right? P is a polynomial. P of x is a sub n x to the n, maybe it's lowercase n, usually people do, plus a sub n minus 1 x to the n minus 1 plus down to a sub 1 x to the 1 plus a 0, where all the where a0, a1 to an are all real numbers. So these are all constants. And let's say that the top term is not 0, is called a polynomial of degree n. Polynomial of degree n. So n is, n is some natural number. Okay. Right. So this is just like a general form that any polynomial will fit into. Right. Any polynomial is going to look like this. Right. So if you give me an example of a polynomial, right, p of x, let's say f of x is x squared plus 1, right? Well, that falls into this form, right? It's the case where n is 2. That would be this would be of the form a2 x squared plus a1 x to the 1 plus a0, right? Where your a2 is 1, a1 is 0, and a0 is 1. Right? Right. So this falls into this, it fits into this description. Okay. So any polynomial that you can think of will fit into this description, and these are all the polynomials. Okay. So this is how one describes a polynomial. Right. Okay. Okay. So those are polynomials. That's a definition of polynomial. You see that it's a pretty precise way of describing, right? Rather than saying, well, it's got some powers in it, or well, it's got some variables or something or other. So there's a way of talking in mathematics, right? There's a way of mathematical language, basically. So you'll get it's helpful, I think, to look at these examples of how we define things and start to think in this way. Like, how do you describe something? Well, what's a polynomial? Well, it's going to be sums of powers of x, right? It'll take x to some sums of powers of x, and with some coefficients on it, right? What are the coefficients? Well, those coefficients are constants. Those are all real numbers, right? Right. So this is a function, and maybe to be very proper, I should say, it's a function from R to R, right? To indicate that the x is also a real number, And of course the alpha is a real number. So any function p with domain R and range R of this form is called a polynomial of degree n. Okay, another definition, if p is 0 at some point, we say x naught is a root of p. Okay. So wherever p reaches 0, we call that thing a root or a 0. Okay. We call it a 0. Right, for example, this polynomial that we wrote up here, does it have any zeros? Is there any place where this polynomial is 0?
And x equals 1.
At x equals 1? When you put in a 1,
Sorry.
you get 2. Right? Any place where this polynomial is 0? This polynomial doesn't have any zeros, right? If I had this polynomial, say, which is the one I think Cynthia is thinking of,
Yeah, sorry.
right? Then this polynomial has zeros, right? Where 1 and negative 1, right? 1 and negative 1 both are zeros of this polynomial, right? Okay, this sort of leads us to this following fact, which is called the fundamental theorem of algebra. Fundamental theorem, abbreviated theorem. It's a fundamental theorem of algebra. So every polynomial with real coefficients, which are the ones that we are going to be dealing with. So in this course, everything is real. We're not going to be talking about complex numbers. Okay, so real numbers only. Every polynomial. Now that I've said that, I don't really need to say this, but with real coefficients can be factored into a product of irreducible polynomials of degree less than or equal to 2. Okay, and by irreducible, I mean that they can't be factored any further. Okay, you can't factor them. You can factor them down to a certain point. You can any polynomial you can break down into a product of polynomials of smaller degree. They'll all be of degree 1 and degree 2, and the degree 2 guys can't be factored any farther. Okay. Here's an example. X cubed plus 3x squared plus 7x plus 10 actually has negative 2 as a root, and factors like this. So this degree 3 polynomial turns out that you can factor it down into a product of this degree 1 guy and this degree 2 guy, and this degree 2 guy can't be broken down any further, okay. Unless you use complex numbers. Okay? If you use complex numbers, then yeah. If we're doing complex numbers, then this statement is really everything gets down to degree 1. Okay, but over the reals, you might have something like this that can't be broken down unless you use complex numbers. Okay. Okay, so this is a famous result, the fundamental theorem of algebra. We're just gonna just keep it in mind. It's just a fact that will be useful, but we're not gonna prove it. To prove it, you have to. One way to prove it is to. One way to prove it is to, this is why I have 4 boxes of chalk. One way to prove it in your undergraduate career is to if you get up to a course in complex analysis, then it's proven in that course in a really beautiful manner. Okay. So it's some ways away, but you know, if you wanted to get there, you could get there. Okay. So complex analysis is sort of like you redid your calculus from a completely different viewpoint, and then in addition said we're going to do everything over complex numbers. Okay. And it turns out that once you demand that you have complex numbers, for some reason everything works out really nicely. A lot nicer than if you just stuck to the real numbers. It's sort of interesting. So that's sort of an early on upper level course that people enjoy because of the simplicity that results. Okay. So anyway, there's this fact. Polynomials can be factored. Okay. Okay. Everyone all right? Any questions? Any questions so far? Just for your amusement. One way that people factor this is to maybe you figure out somehow that maybe you guess a root. So maybe by some sort of guessing leads you to see that -2 is a root. Once you have the root, then you use long division to factor, right? Because if this is factorizable, then you should be able to divide out, right? So you divide out. You should be able to divide out the factor, right? So once you guess the root, then you say, okay, well, let's figure out what the product is. So you get 3x squared plus 7x plus 10. You don't have to know this, but it may come in handy at some point in your life. Then you would do long division, just like you did long division for numbers, right? So like here, I'd say x squared, right? And I multiply x cubed plus 2x squared. I subtract, just like I do when I'm dividing numbers. I get x squared plus 7x, right? And I get plus x. I get x squared plus 2x. And I get 5x plus 10. 5x plus 10, and you say 5. Right, so it divides cleanly. You see that this thing, is the product. Is 2. Okay, so you can do long division. The digression here is that one can do long division with polynomials just as you do with integers. Rachel?
How would we factor that if you didn't know one of the roots to get on division?
If you didn't know one of the roots, then it's hard actually. It's hard. So there are a couple ways. Do people know any other ways to guess a root? They used to teach this. Hi, Cynthia.
It's like P over Q.
P over Q, yeah. If there are any rational roots, then they will be a factor of this guy over a factor of this guy. There are various ways of guessing roots. If there are any roots that are in the rational numbers, then they have to be of a certain form. For cubic polynomials, there is actually a formula just like the quadratic formula. For the quadratic formula, you've got you know how to find the roots. There's actually something like that for the cubics. And there's a formula like that for quartics as well, for fourth order polynomials as well. And these were all I forget, maybe it was the 17th century? During the 17th century, people would discover these things and then hide them from others because they wanted to be the possessors of their own knowledge and not share it with other people. And so you might wonder, what about 5th degree polynomials and what about 6th degree polynomials? Are there formulas for that? And maybe people worked on those as well. But in fact, it was shown that you can't do it. You can't do it for 5th degree and higher, I think. There's a story involved with it. So that result was actually done by the French mathematician Galois, who died at age 21, actually. So he was he was not only a great mathematician, but he was also very involved in politics. And I think it was right after the French Revolution, he was somehow framed for his activities, and then challenged to a duel, and then killed. The night before the duel, he sort of knew that he was going to die in this duel. And so the night before the duel, he spent the entire night writing down all of his mathematical ideas. And they still have this note. It's furiously scribbled. He's writing down everything that he's thought of. And he has so there's this letter from Galois. That letter basically influenced the next 100 years of mathematics. Trying to puzzle out what he was doing and figure out his ideas, which led to the resolution of this problem about the fifth degree polynomials and above. Basically changed mathematics. So people always say, here I am, X number of years than Galois was when he died, and what have I accomplished? That's how we all feel constantly. Okay. Some other things that you've probably seen before, just some naming, nomenclature. So just some names. Right? If f of x equals f of negative x, right? We say f is what? If f has this nice property that whenever you evaluate it at some point x, and you evaluate it at negative x, they have the same values, right? Then you call this function even. Mm-hmm. So f is even. If f of x equals negative f of negative x, we say f is, of course, odd. Right? Can somebody give me an example of an even function?
X squared.
X squared. Can somebody give me an example of an odd function?
X cubed.
X cubed. Is that a coincidence? No, of course not. Right. Can somebody give me an example of a function that is even but not a polynomial? Can somebody give me a function that is even but not a polynomial? Maya?
Cosine of x?
Cosine of x. Great. That's great. Cosine of x. Right? So cosine of negative x is cosine of x. Right? But cosine is not a polynomial, at least it doesn't seem to be one, but later on you'll find out that cosine actually can be expressed in the following form. 1 plus x squared over 2 plus x to the 4th over 4 plus x to the 6th over 6 plus x to the 8th over 8 factorial plus et cetera, infinitely. So in fact, it's an infinite sum of even degree monomials. Okay, and similarly for the sine is an example of an odd function, but it doesn't seem to be a polynomial until you take calculus 2, at which point you find that it actually is an odd polynomial. Wait a second, what am I doing? This should be minus, plus, sorry, it's alternating signs. And then here you get x minus 3 factorial plus 5 over 4 factorial plus minus, etc. Okay. So anyway, just for your amusement. Okay. So yeah, odd functions, even functions, right? You know what they look like, right? Even functions reflect, are symmetric about the y-axis, and odd functions are symmetric about the origin. Okay. So things you've seen before, some things that you've seen before. Generating new functions from old functions. So you can, one way to do it is to use arithmetic, right? So plus multiplication, multiplying by some number, and dividing. So, so for example, if f of x is x squared minus 2, g of x equals x plus 3, right? But if I write something like h of x is f over g of x, all I mean is that this is going to be x squared minus 2 over x plus 3, right? It's going to be the ratio of the two functions, right? As you expect, right? If I write h of x is 5f plus g of x, then of course all I mean is that you get 5x squared minus 2 plus x plus 3. Wait, as you think. Yes, Rachel.
You're saying that functions in arithmetic, what's like the second to last sign?
All I mean is multiplying by some number. So if I have 5f here, all I mean is you've got 5 times f. This alpha is going to be some number. That number is an alpha. That letter is an alpha. Okay. One usually uses alpha when one's describing multiplication by some number. Okay, so this is a very simple way of generating new functions from old functions, right? I have these two functions, and then I make up some other functions just by combining them. Okay. Nothing. Okay. Okay. There's another. So that's one way of combining functions. Another way of combining functions is via composition, right? Right. What's composition? What do I mean by composition functions? Samantha?
It's like one function you input it into the other functions, it's like f of g of x.
Right. So you take the output of one function and you take that as the input of the next function, right? So you have the picture one can have in mind is like this, right? You have one function f going from the reals to the reals, and you have another function f g going from the reals to the reals, right? And so you create this combined function g composed with f. Okay, g composed with f is going to be you take the output of f and you feed that into g. Right? You take the output of f and you feed that into g. Composition of g with f, written g little circle f, means that you take g and then feed the output of f into it. Okay? So you see what happens, right? You start with some point x here, and then you run it through f first, and you run that output through g, and you get g of x. And so this function here is the composition function. Okay, so for example, if f of x is x squared plus 1, and g of x is the square root of x, then what is g of f of x? And what is f of g of x? And you take 20 seconds and write down something. Okay, turn to somebody next to you and say what you wrote.
Okay.
Okay, who would like to tell me? Who would like to tell me what the first is? Arichka?
So g of f of x is equal to the square root of x squared plus 1.
Mm-hmm. Right. So it's going to be g of f of x. Right. F of x is x squared plus 1. So I'm feeding this thing into the square root function. I get the square root of x squared. Okay. Okay. And what about the second one? Naomi?
It's the square root of x squared plus 1, which is x plus 1.
Square root of x squared plus 1. Mm-hmm. Right. Right, because you're gonna take f, right? F of the square root of x, right? So that's the square root of x squared plus 1. F of x says I'm going to square whatever you give me, and then I'm going to add 1 to it. Okay. So let me just make one caution here. What's the domain of the first function? What's the domain of the composition g of f? This part is not the caution. All reals, right? It's okay to feed in any number here, right? Because when you square it and add 1 to it, you take the square root of that, that's still legitimate, right? Because you're going to get a positive number, and you're feeding a positive number into it. Right? Okay, what about the second function? Has to be greater than or equal to 0, right? Even though you might say, isn't this the same thing as x plus 1? Right? Isn't this the same thing as x plus 1? It's not exactly the same thing as x plus 1. Okay. Because it's this composition. And so not. So you have to be a little bit cautious about the domain. Right? The domain of f composed with g is all points in the domain of g whose images lie in the domain of f. Okay. All points in the domain of g whose images lie in the domain of f. Basically, any point that makes sense when you run it through both functions, right? But it's just common sense, right? Any point that results in an answer, right? Which turns out to be all points in the domain of g whose images lie in the domain of f. Okay, so just to make this completely clear, let's do one small example. G of x is x plus 2, and f of x is the square root of x. Okay. What's the domain of f composed with g? Think about it for 10 seconds. Say. What's the answer, Esme?
X is greater than or equal to -2.
X has to be greater than or equal to -2, right? So the domain is everybody who's greater than or equal to -2. Because it's everybody in the domain of G. Well, the domain of G is all numbers, but you need guys for which the output lies in the domain of F, right? So x plus 2 must be greater than 0. In other words, x must be greater than -2. Okay, so it's simple. X plus 2 must be greater than or equal to 0. Right? The output here must lie in the domain here, the domain of the second function. Okay. Any questions? Should I go faster? Should I go faster? Slower? Should I take a poll? Maybe I'll take a poll. Everybody close your eyes for a second. Raise a finger if you want me to go faster. Raise a finger if you want me to go slower. Okay, open your eyes please. Thank you. So basically okay. Okay. Something else that you've probably seen before, translations. Given f, one can define a new function. G of x being, say, f of x plus some number. Right? And this thing is called a horizontal, this guy is called a horizontal translation. So, what does this look like graphically? Can somebody tell me what this corresponds to graphically? Right. If f is, suppose f looks like this. Is f, right? And let's say that h is a positive number. Okay. Let's say that h is positive. It doesn't have to be, but suppose for this example that h is positive. Right. So what does graph of G look like? Madeline?
It's the same graph, but h units to the left.
Mm-hmm. So it'll be the same graph, but h units. So this distance is h here. It'll be the same graph, but just h units to the left. Right. Right. G of x is doing what f of x is doing h seconds later. Right? G of x, G does whatever f is doing, but ahead of time, h seconds ahead of time. So here, in this picture, h is some positive number, like here's h. Okay, so translation, not particularly exciting. Another example. Let's suppose you have some other function k. You have some function that's f of x plus h. Right? What does that function look like? What does that function look like? Somebody who hasn't spoken, Emily?
It's similar things, but shifted up.
Shifted up. Right? So you just shift the whole thing up by h units. Okay, so here, shifted up by h units. Okay. So that would be, this thing is k, and this thing is g. Okay. So this is called a vertical translation. Vertical translation. Okay. It's not. It will not be that significant. It will not be that important. Okay. Here is something that will be more important. Something called parametric curves. Okay. So here's what it is. Here's the definition. So given two functions f and g from R to R, we create a function gamma. This is a little gamma, a little g in Greek. And this function will be defined like this. Okay. So it's a function from R into the plane, from the line into the plane, right? So goes from a line into the plane. Okay. And it takes the point t to some point f of t, g of t. Okay. So as t changes, then the coordinates of that, the coordinates which are f and g, the coordinates change. Okay. So you can think of it as something that describes a curve, right? A curve, or you can think of it as a point that's walking around in time. Okay. So the image of gamma, that curve that's generated, is said to be parameterized by x equals f of t, y equals g of t. So interestingly enough, this word parameterized almost did not exist a few years ago. It was always spelled parameterized. But I myself have never liked that spelling, and I've always spelled it in this way. And now it is spelled this way. So I don't claim to have created this word. Like my brother claims to have created the word haughty. But yeah, he says that he's the first one who used the word haughty whenever. But anyway, I'm glad that this word exists. Yeah, and I don't mean to imply at all that my brother is some sort of social animal or something. So, yeah, he's as you can see, he's probably not. Okay, so some examples of parametric curves. So if I have something like this, f of x, f of t is t and g of t is t, then the parametric curve that we get, well, what's that? That will be, t comma t, right? It'll be t comma t as t ranges over the reals, right? Well, what curve does that describe? T comma t, right? Right? Here's time 0. At time 0, it's going to be at 0, 0, right? At time 1, it's going to be at 1, 1. Right? Time 2, it's going to be at time negative 1, it's going to be a negative 1, negative 1 line. It will describe the line y equals x, right? So it's going to walk around on this line here. Right? It progresses from here. It describes the line y equals x from the lower half to the lower left to the upper right. Right. Okay. Here's another example. I'm just going to write it in shorthand. So f of gamma of t is saying t squared t squared. T squared t squared. What is that? Suki, was that you? Was that you? No? Nope. So at time 0, let's see, we're at 0, 0. And then at time 1, we're at 1, 1. That's and then time 2, we're at 4, 4. Right? At time square root of 2, we're at 2, 2. Right? So where are we? What is this tracing out? Emily? Oh yeah, that's right. So so this would be the absolute value function, right? So here it's going to go up like this, right? And then at the negative numbers, it gives you. Well, wait a second. No. I'm sorry. It's not a p, right? So as your numbers head towards 0, you head towards here, and then as you get to negative numbers, what happens? You just head right back up,
Yeah.
right? So this just covers it covers the ray twice.
Wait, how can you say that if it is gamma, right?
Mm-hmm.
Gamma of t, the x value is t squared.
Yeah. So right. So gamma at -1 is going to be what?
But it's by saying gamma of -1 isn't the x value -1.
No, the x value is t squared, right? So gamma of t. So you feed it a -1, it'll be like -1 squared, -1 squared. Right? So 1, 1.
But then isn't that a different x that you're using? So how can you like if you
This is not your x value. This is not your x.
of an x value, function of an x value. Right?
Yeah. So this is right. This is the input,
Yeah.
right? But that input. We're not drawing a graph. We're not graphing this function here, right? We're not graphing this function. We're looking at the image of the curve, which is something quite different.
Okay.
Yeah. So right. So you think, well, at time 0, maybe it's best to draw the picture again. So here. Right. So gamma goes from here into here, right? And at 0, it's going to be at 0, 0. At -1, it's going to be at 1, 1. At -2, it's going to be at 4, 4, right? And as you head backwards in time, then this thing shoots off in this direction.
Okay, so if you weren't using gamma, you're using a real equation, what would that look like? What are you going from? What is gamma on a number line? I'm confused.
I'm not sure of your question. Say your question again, and maybe I can.
What is gamma, like not as just saying gamma, but as saying like a real function? Like what's a real example of this?
This is a real example. I mean,
But I mean like using like an actual pair, not like an actual polynomial. Or is it not?
Are you asking, can you write this as a function?
Yeah.
No. This is something different. It's called
Right.
so don't think this is not a function.
Oh, right.
Okay,
Okay.
not a function. Yeah, not a function. This is something else
Right.
called a parametric curve. Okay, and so parametric curve is not. It's rather you think of it as you have this point and it's traveling around on the plane. Okay, and you look at the curve is the collection of all those of that path that it describes. Okay. Let's see. So here's another example. F of t is t, and g of t is t squared. Don't say it. Do you know it already? Don't say it.
I just have one
You have a
question.
question? Okay, great.
Yeah, so saying that it's like the point that travels around on the graph.
Yeah.
So the plane, would that kind of be like an etch-a-sketch?
Yeah, exactly. Yeah.
Okay.
So and the input is time. Okay, so at a certain point in time, t is keeping track of the time, and the position is your x and y.
Okay.
Right.
All right, that makes more sense.
Okay, good. Okay, so take a look at this one, right? If gamma of t is f of t, g of t, then what curve does it describe? What's the image look like? What does the image look like? Ellen,
Graph of y equals x squared.
look like the graph of y equals x squared. That's actually, so why do you say that?
Because if it were in like
what do you call y equals x? Like, what do you call that
Like
system? Like,
Cartesian?
yeah, if it was in Cartesian, like f of t would be x and g of t would be y.
That's right.
So you're squaring the x values, which should be y with x squared.
That's true. So you notice that there's a relation between the x value and the y value, namely that the y value is the square of the x, right? The y value is the square of the x. So this thing lies, by noticing that, you know that the image lies on the parabola. Okay? The image lies on the parabola. You don't necessarily know that it's the whole parabola, but you know that it lies on the parabola. The image, the curve is on that parabola. In fact, it is the whole parabola, right? If you start out with t at 0, say, right, then you have 0, 0, right? With t equals 0, you have 0, 0. At t equals 1, you have 1, 1, right? 0, 0, 1, 1. And then at 2, you have 2, 4, right? So at time 2, you're at 2, 4, right? At time 3, you're at 3, 9, right? At time -1, right? You're at negative 1, 1. At time -2, you're at -2, 4, etc., etc. Okay. Okay. So this one, the t and the well, anyway. So it turns out to be, you know, the parabola y equals x squared. Okay. So this one turns out to be a function. They need not be functions. Let me finish up with one last one, which I hope you get, and which will lead into the next section. Gamma of t is cosine t sine t. What's this? Does anyone know immediately? Cosine t sine t, as t ranges over the reals. It's a circle, right? It's a unit circle. Right. So it's a unit circle. Right? At time 0, you're going to be at 1, 0. Right? And as time goes forwards, as you have to time pi over 2, you're here. Time pi, time 3 pi over 2, time 2 pi, and you keep on running around, right? So this thing covers the circle. As time goes forwards, you keep on racing over the circle in a counterclock, chasing over the unit circle in a counterclockwise manner. Okay, and as time goes backwards, you go in a clockwise manner. Okay, that's it. Let me try and get some homework back to you. Okay.